Good morning, good afternoon, good evening, whatever you are. Thank you so much for joining us. My name is Lilian. I'm the scientific coordinator of POGO, and I also coordinate our alumni network, the NF-POGO Alumni Network for the Ocean, or NANO. So before I introduce our speaker, I will ask 3 minutes of your time just to introduce NANO to those who are not familiar with our organization. So NANO is a network composed by former and current scholars of NF-POGO trainings. And the objective of our network is to maximize the benefits and extend opportunities from beyond the trainings. So NANO dedicates activities towards the networking and collaborative initiatives by our members. And these include research projects such as the NanoDope, which is a short to global study of deoxygenation, ocean acidification, and productivity at select sites. Basically, the NanoDope project runs a network of coastal monitoring stations, all led by our members in 18 different countries. So we currently have 33 stations in those countries. And we support sampling monthly or bi-monthly of essential oceanographic variables on these stations. Also support remote sensing analysis from the stations, and our members are engaged in capacity development, outreach, and citizen science initiatives at those in their nations. So one of the capacity development activities of this project includes this webinar series, where we invite friends and members of the network to give talks that are of interest of early career ocean professionals from around the world. So today, our webinar is going to be presented by Anna. Anna is a PhD student at the Fisheries and Marine Institute of the Memorial University of Newfoundland. She's an oceanographer specialized in sustainable fisheries, bycatch reduction, trophic dynamics, and data-driven approaches to ecosystems management. Anna has a master degree in biological oceanography, and she also has a bachelor in oceanography from the Federal University of Rio Grande in South Brazil. And she joined NANO after she successfully completed the Center of Excellence for Observational Oceanography, which is now based in Canada. And Anna is actually a trainee from the first year of the training in Canada. So before I pass to Anna, I want to thank her and thank you again for your presence, and to inform you that this webinar is being recorded. We're gonna later upload the recording on YouTube. So you can go to our YouTube channel, or actually to the POGO YouTube channel, and rewatch this and all the other previous 30 webinars that this series has promoted. You can get more information on NANO on our website and on our social media. And that's it for me. Thank you.
Hello everyone. My name is Ana Júlia, and today I'll be talking about a project where I evaluated the catch efficiency and the ecological impact of a novel double-wheeled trawl footgear. And we will follow this journey from the concept to sea, so basically from the initial idea all the way through what happened when we put it in the water. And I was going to make myself a quick introduction, but Lika already was very thorough on it. Thank you very much. So I came to Canada through the NF-POGO Centre of Excellence program in 2024. And it was through this fellowship that I met Doctors Tomás Araya-Schmidt and Dr. Paul Wenger. They introduced me this project, which I developed during the program, to evaluate a novel trawl footgear for the northern shrimp fishery. And well, without further ado, To understand why this project exists, we need to start with the problem. So bottom trawling is one of the most widely used fishing methods in the world and is economically important and feeds millions of people. But it comes with real ecological costs. Three main ones are first is bycatch. Bottom trawling alone accounts for 25% of global discards. And in shrimp fisheries, up to 50% of what comes up in the net can be non-target species. Second is seabed damage. The foot gear, that is the part of the trawl that drags along the bottom, disrupts the benthic habitats and resuspends sediments. And finally, there's also this growing pressure to show that fisheries can operate sustainably with the reduced ecological footprint. So the question becomes, can we design a gear that works just as well but causes less damage? Well, before we go any further, I want to orient those who aren't familiar with trawls. So a bottom trawl is essentially this large cone-shaped net that you're seeing it that is towed through the water. At the front, you're gonna have the headline up top with the floats to keep it vertically open. And the ground, you're gonna have the ground gear or foot gear along the bottom. The two sides of the net that extend from the mouth are called wings, and the foot gear runs along the bottom edge connecting the wings. Well, behind you're going to have the body, the extension, and the caught end, where the catch accumulates. But the part we're going to focus today is the ground gear. So how does the conventional gear work? The traditional trawl that we refer here as control it uses this standard configuration foot gear with discs in the entire extension of the fishing line. So as you can see here in the figure, you can look at how the discs are positioned. They're basically lined up and dragged across the seabed as the trawl moves forward. So in the middle, the discs will roll in the direction of the toll, but as you get to the sides, they're no longer aligned with the toll, so they just drag through the bottom. And the idea is that instead of a single disc dragging along the bottom, what if we paired two discs together, aligned with the tow direction, and so the whole gear can roll over the seabed rather than scraping it. So this is how the double-wheeled configuration came up. We have 14 discs near the mouth and 12 double-wheeled units along the wings, 6 each side. As you can see in this figure, the double wheel units are spaced differently and they're designed to roll rather than drag. And the idea is that would reduce the gear contact with the seabed. Well, before taking to the sea, we need to test the concept in a controlled environment. So we need to build scale models and test them. And here at the Marine Institute, we have the flume tank for that. So as you can see in the photo, the flume tank is essentially a large water channel where we can simulate the towing conditions and observe the gear behavior with cameras. As you can see here, I took this picture. And this is what the flume tank data showed us. Looking at the diagram on the right, you can see that the seabed contact footprint of each gear. So for the traditional gear, 69% had contact with the ground. But for the double-wheeled gear, only 21% did. So that's a 48% reduction in seabed contact, which was very promising. And after that, we built the full-scale versions and headed to the sea. Well, the field trials were conducted in a commercial inshore shrimp trawler in the west coast of Newfoundland. And the experimental design was a pair alternating sequence where A was the control and B was the experimental gear. Each pair of toes was conducted on parallel tracks and separated by 100 to 300 meters to make sure that both gears were fishing under the same environmental conditions. 12 paired toes, so 12 control and 12 experimental, were completed, and they're all done during daylight hours. So what did we measure? Three main things. First was a trawl geometry, so wing spread, door spread. The doors are there to help keep the net open horizontally, and headline height, that is the vertical opening. And they were recorded by sensors every 15 seconds. And these tell us how the gear is behaving physically in the water. We also measured shrimp catch, so the total weight per hectare and the size distribution, measured from a subsample of the catch, and also the bycatch for the three most captured non-target species: capeling, Greenland halibut, and redfish. These three species alone represent more than 80% of the bycatch. We recorded the total abundance per hectare, and we measured the total length up to 55 individuals per toll. So statistically, we used a paired design. The core model was generalized linear mixed models with gear as fixed effect and pair as a random intercept to account for the natural toe-to-toe variability. And for trawl geometry and catch data, we use a walled chi-square tests. For site selectivity, we used a different approach. Spline-based catch comparison models in the select package with permutation tests for significance and bootstrap confidence intervals with 1,000 resamples, and everything was done on R. So now let's look at the results. Starting with trawl geometry. Here we attested that the fishing conditions are essentially identical between the two gears. So wing spread, door spread, speed over ground, and which is the velocity that the net is being told. The depth and the area trawl all show no significant differences. And this is important because it confirms that any differences that we see in the catch can be attributed to the gear itself. However, there was one significant difference, that was headline height. The experimental gear had a significantly higher headline height, so 5.2 meters over 4.9 meters for the control. And that 30 centimeter difference may have some implications, may tell us something, but we'll see ahead. And another thing that it's important to note is that it was observed in the field that something that we were not expecting. So during the holdback, they consistently noticed mud accumulation on the grout gear, the net, and even in the catch. And even though they noticed in both of them, they saw that it was much more frequent in the experimental trawl. And we will come back to what this might mean. So let's go to the catch results. Starting with the target species, the shrimp. Here, the news are very positive. There was no significant difference between the gears. The p-value was 0.9. Both catch around 72 kilos of shrimp per hectare. And looking at the graphs on the right, you can see the length frequency distributions, and you can see that they overlap almost perfectly in the panel A. This is basically the raw data. And the selectivity curve in the panel B is flat and centered right around 0.5. And that means that each year caught an equal proportion at every size class. So this all makes biological sense because both trawls were identical, and the shrimp selectivity is determined by the net and not the Footgear. But the bycatch results tell a different story. For capeling, no difference. 21 individuals per hectare, p-value of 0.9. Exactly what we would expect for pelagic species. But for Greenland halibut, the experimental gear caught significantly more, 6.7 individuals per hectare versus 4.3 individuals for the control. And that is a 50% increase in catch with a p-value of 0.014. And for redfish, same thing. 4.6 for the experimental and 2.7 individuals per hectare for the control. So the experimental caught 70% more with p-value of 0.034. And both of these are demersal species, and that distinction is the key to understand what happened here. So another important question is whether the experimental gear was selectively catching larger or smaller individuals, which would have different conservation implications. The answer for all three species is no. There was no significant length effect for any of them. And panel A shows, as I said, shows the length frequency distribution, which is basically the raw data. And we can see that the same thing that we saw for the GLMs for Greenland halibut and redfish. So more individuals captured by the experimental trawl. That is represented here in the gray line. Panel B shows the selectivity curve and the proportion of individuals at each size class that were retained by the experimental gear relative to the control. So if the curve stays flat around 0.5, as we saw for the shrimp, there's no size effect. If it's above 0.5, the experimental gear is catching more across that size class. For capeling, the curve is essentially flat around 0.5. So no difference as expected. For Greenland halibut, the equivalence test was significant, which means that the proportion retained by the experimental gear was significantly higher across all size classes. And you can see that but the majority of the line is above 0.5, and that only that only part of the line that is below that, it represents one only individual. For okay, I'm done with that. For redfish, the pattern is okay. For redfish, the pattern is similar. With there was a marginal equivalence of 0.57, saying that it caught more, but as we saw for the GLMs, it did caught more. So the take-home message here is that this is a general gear effect. This is a not size-selective retention. So the experimental gear catches more fish across all sizes. And why did it happen? Why did the experimental gear catch more bycatch? So our hypothesis centers around the horizontal steering chains that will connect the double wheels. In the flatfish fisheries, they use these stickler chains, like you can see here in this image from the California Department of Fish and Game, that are dragged along the seabed to disturb the bottom, flush fish out of the sediment, and then herd them into the net. And we believe that the steering chains of the experimental gear ended up doing exactly that unintentionally. The chains were likely dragging and digging into the sediment, resuspending the particles, and ultimately driving more fish into the net. Species behavior supports this hypothesis. Greenland halibut and redfish spend significant time on or near the seabed during the day, specifically, um, which is exactly when we were fishing. Also, more contact of the fishing line with the bottom also physically reduces the space through which the fish can escape under the trawl. And capeling, on the other hand, is a pelagic schooling species, so it was not affected by the higher seabed interaction. And that fact actually it strengthens our hypothesis because this is exactly the pattern that we would expect if the mechanism is seabed related. And this brings me to the ecological matter. The vast majority of the bycatch individuals that were caught were juveniles. So Greenland halibut mostly measured between 13 and 30 centimeters, which is way below the legal size of limit of 44 centimeters. The redfish were mostly between 8 and 13 centimeters. Um, and they need to reach 22 centimeters to actually enter the fishery, and that takes about 7 to 10 years for that. So juvenile fish have very low survival rates after capture and handling. So we we're not just catching more fish. We might be removing individuals that are critical for the stock. So, what did we learn from all this? First is that the experimental gear worked to catching shrimp, so the main goal was achieved. But secondly, it produced way more bycatch of juvenile Greenland halibut and redfish. Third, is that the higher headline height suggests that the gear had more seabed contact than intended, not less. So the engineering really needs refinement. And fourth is it's not a size selective gear, and it catches more individuals across all size classes. But the larger Greenland halibut were almost exclusively caught by the experimental gear. So after 31 centimeters, except for the only individual that we saw in the that were below the line, they're all caught by the experimental gear, which is a pattern that is consistent with this greater bottom interaction. So moving forward, we have three concrete recommendations. The first is to reduce or to remove the horizontal steering chains. And these, because they are the source of the unintended seabed interaction. Second is to retest and the after the modifications in the flume tank before any new sea trials. So that means go back to the beginning of the process and do it all over again. And the third is to deploy underwater cameras during trawling. So we made a lot of inferences from indirect evidence. So we have a lot of evidence, but it it's not really that tangible. So this direct visual observation of gear-seabed interaction could give us a much clearer answer about what's actually happening in the bottom. Well, and that's it. But before finishing, I would like to mention that with those recommendations, it's nice to add that we, of course, don't test only one thing. We keep testing to see which one is more promising. And we do have another one that was tested and gave much better results, which is the aligned Footgear. That project I was not a part of. My supervisors were. So this is my idea here was to show you that we have to do all this, and we, in a frustrating way, we might not find the best results, the best answer, everything that we wanted, because we always, as scientists, we always want everything to work perfectly. But that project only happened, the project that actually showed promising results, because we could uh, recognize the mistakes made in this project. So even though it's a failed attempted, it is also progress. So now, thank you very much for your time and for your attention today. And I hope this gave you this a good picture of this promise and the challenges of this gear concept. I'm happy to take any questions, and my email is on the screen if you'd like to follow up. Thank you.
Thank you, Anna. Very good. My master's advisor used to say there is no bad results, only results. So even if this, and it's not completely bad, right? The catch was the same in the end. So,
Yes.
but yeah, it's a learning progress. So if you have a question, please raise your hand. And I can call your name so you can switch on your mic or just type your question in the chat, please. And I was wondering, and I'm gonna start with my question then. So when you were testing the gear in the pool, the contact was lower, right? Was much lower. What do you think that made this difference that in the sea it actually went higher? That's what we are assuming, right? From what I
Mhm.
understand. Yeah.
Yes, yes. The problem with the control environment is that you're not going to have anything related to what's actually happened down there.
Hmm.
So we can only see the contact in this controlled velocity that it's being told. So that means that if the bottom of the ocean was this flat surface with nothing to be uh, um,
No rocks,
resuspended,
no mud.
yeah,
Yeah.
then it would function great. But we
Yeah.
have
Real
things
life,
that we
it's
can't
different.
really predict. Mhm.
Yeah, and I was planning to ask you if you had the chance to investigate the seafloor after the passage of the trawls, but I understand that this is going to be done on the next trial, right?
Yes, actually, that had happened for other trials.
Hmm. And the headline, so sorry, I made a note here. The headline height, it's
Uh-huh.
from the bottom of the gear to the bottom of the floor, or is that entire
No,
open
it's the entire
aperture?
opening. It's the from the foot gear to the head to the headline. I mean,
Mm-hmm.
uh,
So
Oh, I'm not sure.
Your hypothesis is that it's actually this difference comes in the bottom, and that's why you're getting more
Yeah, so my
bycatch
idea,
and
yes, my idea is that since it's digging the ground, then it's gonna because when we think about that, we're thinking it's always everything is on the ground.
Mhm.
But the dimension of the net is it's really hard to understand. It's really, really big. So you're talking about these discs, and they are, I don't remember they are like 30 centimeters um, diameter.
Mhm.
So technically, it's not the net itself. It's not on the ground. You're gonna have that to help. Um, so if it digs, it might not enter completely, but it will be lower. So my idea is that the headline height was higher because the mud was pushing the wheels, the
Did
discs down.
what was the speed of dragging? I don't know if that's the correct term, but the dragging speed was somehow different between them because that would confirm
Hmm.
that motive,
No,
right?
no, the dragging didn't. No, it wasn't different. But the dragging is most the velocity you're talking about, right? Like
Mm-hmm.
speed.
Yeah.
It was it's controlled by the boat. So the boat it's too strong to have that
Mm-hmm.
slowing it down.
Yeah.
Mhm.
Okay, so we have a question from Santosh on in the chat. So they're asking which gears are commonly used for ichthyoplankton collection in marine environments.
For ichthyoplankton.
It's
Oh,
usually the vertical ones, right? Bongo?
ichthyoplankton. Yes, I think so. Hmm.
Yeah,
Yeah, there are
because
a
they're
few.
so small that you
Hmm.
have to have a very fine mesh.
Hmm.
The yeah, I'm no fishing. My background is far from fishing, but from remembering my undergrad years, it's usually the vertical bongo nets that you
Hmm.
profile. That anyone in the audience or Anna as well, if someone wants to comment on that.
Well, I think that's it too.
Yeah. Any other questions? So you're working on this subject for your PhD, Anna?
No, no, I actually changed completely for my PhD.
Okay.
Um, Now I'm working in a project transforming climate action. So trying to understand the how much carbon, how the carbon's being absorbed by the ocean in the Northwest Atlantic.
Ah.
And my thesis will be about the trophic interactions, trying to understand the trophic transfer efficiency between the trophic levels.
Right. Very good. So, what is the dimensions of the flume tank? This is from Oluwatoyin, from Toyin. What is the dimensions of the flume tank compared with the gear? I think a model of the gear will be preferable. So, were you
No,
testing the real gear on the pool or a
no, that's
model?
impossible. We can't test the rear gear.
Mm.
I guess I went to that part a bit fast. We the idea of the flume tank is not to test the gear itself, is to test the models. So they have this huge, beautiful arsenal of models that are built, and they're not just visually um, similar or equal. They are all the the measurements, the dimensions. So they are made in a way that the model in the flume tank, it's gonna behave the same way that the real one in the ocean. So we have 1 to 4, 1 to 8. I even saw 1 to 70. It's a very tiny one. It's the cutest thing ever. Um, but yeah, the flume tank, about, it's like a regular medium pool, It's not, um, it's very big to be inside of a building, but yeah.
Nice. Okay, another one from Noé Mejia. I'm sorry if I'm butchering your name. There are some pulley systems to up the mesh to the boat, or what is the system they used?
To bring the net to the boat.
Noé,
Uh,
feel free to switch on your mic and ask the question, or
check
give.
over here. I can.
Yes, to the boat, he said, or they
Oh, okay.
said.
No, they have, I forgot the name in English, but they have an equipment that it pulls, it it's very, very strong, because these nets come very full. They're very, very heavy.
Mm. Okay, and Colin answered the question about the pool, the flume tank size. It's 22.25 meters long, 8 meters wide, and 4 meters deep.
Thank you.
Very precise. Thank you. Noah thanks you as well. Any other questions? Yeah, I told you our audience is shy. But this was really nice. It was a really nice example of, real life experiment, and being able to construct something on this magnitude and participate on this
Yes.
must be really
Hmm.
exciting.
Oh, it was amazing. It was amazing.
Mm.
I I was not in the ocean, but
Hmm.
I put together the footgear for the model. Actually, I didn't put together the footgear, but I attached the footgear to the net, and it's amazing to be in there and to understand and to think about that. It's gonna be like, this is we're gonna have one that it's 8 times this size in the ocean. It's
Hmm.
very crazy. Yeah.
Yeah, and it's so impactful. I wasn't aware of the size or the magnitude of, trawl fishing compared to other
Yes.
fishings. And it's something that it's good to hear that people are working on improving something that it's major, like it's essential for that. It's the
Mhm.
main source of protein for the entire globe. It's fisheries, but at the same time, it's so impactful. So it's really good to hear that there are a lot of good people working on improving it.
Yes.
Yes, okay. So there's no more questions, Anna. And I thank you so much for this great presentation and for taking time to prepare it and to present it to us. And I thanks everybody also for joining us and to participate here. Colin says great job and thanks. And I say again, thank you so much. And thanks everybody. Have a wonderful weekend. And don't forget to contact us if you have any suggestions of subjects or presenters for this series.
Thank you.
All right. Thanks everybody and have a wonderful weekend. Bye
You
bye.
too.
Bye.